Hello, everybody, and Happy New Year. A great way to start 2025 is to do Euler's proof that there are an infinite number of primes. This proof uses some very cool ideas, such as the combinatorics of primes. I'll show you two examples of that. Also uses our favorite functions, log of x, 1 over x, harmonic numbers, 1 over k, and a bit of calculus. Euler throws in geometric sum also, and some very clever estimates using inequalities. Very clever. Okay, let's get to it. We will start with combinatorics. Suppose we have just two primes, 3 and 5, and we want to construct all these combinations like 3 power a times 5 power b, let's say. So for example, 3 power 1 times 5 squared, 3 power 0 times 5 cubed, and so on. Even something like 5 power 0, that's 1, or 3 power 0, 5, 0, that's 1. So all those combinations. Now let's put a limit on how far we can go. So let k, big K, capital K, be the largest power. And then, of course, our exponents a, b are going to be between 0 and k. So we want to find a way to generate all these combinations, 3 power a times 5 power b, and there is a nice way to do it. Let's take k as 3 just for now, because it's easy. And let's write down some products here. So I took here the prime 3 and I wrote down all these powers up to k. Big K is 3, and the same for 5. Now any combination I want, I can construct it. For example, let's say I want 1. 1 is 1 times 1, yeah? And okay, let's say I want 3 power 2 times 5 cubed. Oh, well, that's easy. That's this one times this one. And the biggest one is going to be 3 power 3 times 5 cubed. 3 power 3 times 5 cubed. So I've got them all. And it creates a sum. 1 plus 3 plus 5 plus, say, 3 times 5 plus 3 squared times 5, and so on, like that. So we can write it in a sort of a special way. Like this. So I'll use this summation notation. So all a, b powers from 0 to 3, all these possibilities, I sum them all up, and I get this. This is exactly the same as this here. Okay, so that's the key idea behind Euler's proof. This is a key idea in number theory in general. Now, instead of 2, 3, and 5, let's say I have many distinct primes. So P1, P2, and so on up to PR, they are different primes, and I can form the same kind of products, 1 plus P1 squared, all the way up to P1 power capital K, that's my limit, times 1 plus P2, that's my largest power that I want to deal with, P2 squared plus plus P2 power K, big K. And this keeps going all the way. I've got R terms because I have R prime. So the last, not terms, but factors. PR plus PR squared plus plus PRK, like so. And I can now create, by expanding this product, I create a sum that has every possible combination of the powers of these primes. And I can write it like so. So I have the sum, all these powers, AJ, are from 0 to K, and each term has this form like this, A1, P1, A1, P2, power A2, and so on up to PR power AR. Okay, great. So I have every possible number that I can make with these primes up to the power limit of K. So if I want to create this kind of sum, well, I can do it by expanding this kind of product. So this is a genius idea. I think Euler noticed this. He used this many times in proving things in number theory. Okay, and we can write this in a more compact way, like so. I have my k plus 1 powers from k is 0 to k. That's k plus 1 possible powers of the prime pj. I multiply all these things out, I expand all these things out, and I get this. So I get this sum here for all powers, and the form is like this. So this is a beautiful combinatorics type result involving prime numbers. This is very, very nice. And I think if you look at this carefully, the following is also true. If I replace every pj with its reciprocal, so I do something like this, I replace pj with 1 over pj, I get this over here, and this is the second one here is equally true as the first one. I'm sure you could see that. There's no difference in algebra. If I repeat the same argument here with 1 over prime, it is exactly the same thing because they factor the same way. So these two are very beautiful combinatorics type results about the way primes combine to form numbers. All right, that was pretty productive. So let's continue with combinatorics. Suppose I have this sum of numbers up to n is 25. And let's think about all the primes that are in here. 2, 3, 5, 7, 11, all the way up to 23. So this is P1 and this is PR. And all of these numbers are made of these primes. I mean, think about it. It's a fundamental idea in arithmetic. They have to be made of the primes that are less than or equal to n. So what's the highest power, k, that appears in these combinations of primes? Well, I think it's 2 power 4. It's 4. Because 2 power 4 is 16, and that's in here somewhere, but 3 power 4, that's 81, and that's not in this sum, so we can say k is 4. So I get the following very interesting inequality. Well, it's got to be less than the right-hand side here. The right-hand side is all possible power combinations of these primes up to the power limit of 4. So why is this bigger? Let's think about it. Well, something like 2 times 5, this is in here. 10 is in this sum, but something like 3 power 4, that's not in this sum. And something like 13 times 17, that's not in this sum. But yeah, we do have 2 times 5 in here. That is possible. We just take the primes 2 and 5 and then set the other exponents to 0. And we also have 3 power 4 that is in here, and 13 times 17 is in here, and even something like 13 power 4 times 17 power 4 is in here. So of course this right hand side here is going to be much bigger than this left hand side. Okay, so this is an interesting inequality. It's a bit hard to understand at first, but when you sort of analyze it, it becomes obvious. And we can write this in a more general sense. So now I have a sum on the left-hand side up to n. And these primes are all the primes that are less than or equal to n. And here, not 4, but k. K is the highest power that appears. K is highest power. Okay, that appears in this sum here. So this is always going to be bigger than this over here. All right, so now what do I do? Well, so now I apply that combinatorics identity that I derived from part 1. So what I did is I used the combinatorics identity. I took this and I got rid of it. I substituted it for this, the other side of that identity, and I got that. And this is a very beautiful inequality, very interesting. And I'm sure that you can see that this is also true when I substitute for pj. I substitute 1 over pj. I want you to repeat this argument, take a piece of paper and go through the whole thing and get the following result. I get this. And this is the thing that we need to continue with Euler's proof. Now, can you imagine if somebody just threw this onto your desk just like that? You'd say, well, where does this come from? It may be, in a sense, obvious now that we did all this thinking about it, but it really isn't an obvious thing when you see it for the first time. All right, next is calculus. Now let's do a bit of calculus. Let's look at a plot. So this is the curve. Y is 1 over u. This is y. This is u. And let's take x somewhere in here. This number here is an integer. That's the integer part of x, and we'll call this n. All right, so this is the nth harmonic number, 1 over n. This is 1 over 1, 1 over 2, and so on. Now, let's see. Let's do a bit of calculus. Let's integrate this region all the way up to x. Okay. So if I do that integration, that's just routine calculus, 1 to x, 1 over u du, and that's log x. Very interesting. Okay, great. Now let's take a more discrete look at this. I've got the same plot, but now I have some rectangles. All right, so that's x, this is n, this is an integer part of x. And these rectangles, they all have a width of 1. So it's easy to compute the areas of these things. So what is the area of this one? Well, the area of this one is just 1 over n times 1. So that's the area. Area. Okay, and so the area of all of this stuff here, all of these rectangles, it's just the sum from j is 1 to n, 1 over j times 1. Yeah, but we could just get rid of the 1. And I'm sure you can see that this is always bigger than the left-hand side. So this is a beautiful inequality. So this is clear by geometry. This is a beautiful inequality which Euler used in an amazing way, as you will see in the next part. Well, I can even make this a bit more explicit. This is 1 plus 1 over 2 plus 1 over 3 plus so on and so on plus 1 over n. And I'm sure you're starting to see right now, hey, this is something that is related to what we proved in the part previous. And now for the grand finale to usher in the new year 2025. We just proved this inequality where n is the integer part of x using some calculus. But in the previous parts, we also proved that this here is less than or equal to another expression. There, remember this? The combinatorics result inequality using the 1 over pj. So that's true, but what's also true is that if we extend this to infinity, this is even bigger. And so this inequality also holds. And all of these pj, they're bigger than 1. And so this actually is a geometric sum that converges. And we have the following result here. Like this, 1 over 1 minus 1 over pj. The 1 over pj is my geometric sum factor. And I can rewrite this a bit like this, pj over pj minus 1. And even more so, I can do more transformations to this. Let's write it like this. Okay, so it's just a bit of algebra, and you get from here to here. And you got to give Euler a lot of credit for seeing his way through all of this to get to a result that he really wanted. And this is the result he really wanted. So now let's look at an interesting phenomenon. Let's look at primes, pj, and their position. So 2 is the first prime, and 3 is the second prime, 5 is the third prime, 7th is the fourth prime. And so we have the following, that the prime j is greater than or equal to its jth position plus 1. And that's interesting. So p j minus 1 is greater than or equal to j. And so 1 over j is greater than or equal to 1 over pj minus 1. So then this is going to be bigger. Look at the genius of this man. Euler was a human computer. Well, I mean, computers are not very clever, and Euler had the abilities we associate with computer algebra systems, but he was human also, and that made him so formidable. So we have this, because this is bigger than this. All right, so let's continue. We'll do yet more transformations. So we have from j is 1 to r, j plus 1 over j. Great. And we can start to compute this. Okay, so that's 2 over 1 times what? Times 3 over 2 times 4 over 3 times and so on until r plus 1 over r. Now, let's look at this, and we see that everything cancels out in an amazing way, and we get r plus 1. Right. I mean, could you imagine something like this? Euler, amazing. So we proved that log of x is less than or equal to r plus 1. Okay, so this is the critical idea. So we have this. Now, let's assume the following. Let's assume that the number of primes is finite, and let's say there's big R of them. Well, this little r is the number of primes less than or equal to x. So r is, let me write that neatly, number of primes less than or equal to the integer value of x. But this, if primes are finite and r is the largest number of them, then this must be less than or equal to big R. And so therefore log x must be less than or equal to r plus 1. All right, so what's wrong with this so far? Seems reasonable. Well, no, it's not, because r plus 1 is a constant. This is a finite number. This is the biggest one. So r plus 1 is a constant. And so therefore log is bounded. Log x is bounded. And we know that log x goes to infinity. It's not bounded. And so this is a contradiction. There we go. And so it cannot be that primes are finite. Whenever we do these proofs about infinitude of primes, we're not actually directly proving there's an infinite number of them. We're proving that it's not finite. It's an interesting philosophical distinction. It's very interesting. So log x is bounded, and this cannot be true. That's a contradiction. So therefore the number of primes cannot be finite. And there you go, Euler's proof of the infinitude of primes. It's an amazing proof because it has so many fantastical ideas all weaved together in an amazing way. This is a great way to start the new year. Start it with a non-trivial proof of a beautiful theorem. It's so totally amazing. And I think I'm going to talk about primes more because, the more I look into it, the more stuff I see that's really worth talking about in videos. So I will see you next time.